Welcome students to Chapter 21, Part B, where we're going to look more specifically at the humoral and cellular responses of your immune system. So looking a little bit more at that adaptive immune system. We're going to look at the humoral responses first and then look at the cellular immunity with the T cells. So let's look at the B cells first. When an antigen binds to a receptor on the B cell, that will activate that B cell. They'll go through that whole clonal selection process where they make more copies and more copies and more copies of the specific B cell that has the specific receptor for the specific antigen that was activated. Those B cells that we have thousands of copies of now will then differentiate into either an effector cell or a memory cell. So the effector cells are the plasma cells, and they're the ones that actually secrete the antibodies that provide the humoral immunity. And then some of the B cells will become memory cells, and those memory cells are responsible for giving us a secondary immune response if we see that specific antigen again. So let's look at what that kind of looks like in a figure. So we're going to look at the primary response first. That's what this whole figure is looking at. So here's our little antigen. You can see here is the antigen binding to the specific receptors for this specific type of antigen. This B cell here and this B cell here don't have the specific receptor for this specific antigen, and so they don't respond. They're not activated, but the B cell that has the specific receptor for this specific antigen will proliferate, make lots of clones, and just thousands and thousands and thousands of these. Each of these clones will then differentiate. They'll either become the plasma cells, the effector cells that are going to secrete the antibodies, or they're going to become a memory cell. So these memory cells kind of remain in the body and remain in the blood and in the lymphoid tissue, and if they see and encounter this antigen again, we already kind of have some ready to go and ready to respond, as opposed to having to respond and then proliferate and so on and so forth. And so you'll see in just a moment that we have a much stronger, quicker response in a secondary immune response if we see that and encounter that antigen again. So let's look at that secondary response. So now we're going to follow this particular little B cell into a secondary immune response, which is when we see that same antigen all over again. So here we have the same antigen that we saw in the previous figure, but we already have lots of clones already that are have already seen that antigen. They already kind of know what it does and where it's going to do. And this secondary response can be years and years later. It doesn't have to be within a few weeks. I mean, it can be decades later, and you'll still get this stronger secondary immune response. Here is our memory cell. It's been challenged by the same antigen again, and just like in the previous figure, some of these clones will become effector cells, plasma cells, that secrete antibodies, and you can see many, many, many more effector cells than we saw in the primary immune response. And some of these cells will then also become memory cells that will still remain, and we can get another secondary immune response if that antigen were to be seen for a third time. So let's look at what these immune responses look like. So here's the primary immune response, and you can see here's your first exposure to the antigen, and it takes not quite a week before we're really starting to get the production of antibodies for that particular antigen. And you can see it peaks about maybe 10 days is really when we're getting the highest amount of antigens, or antibodies, excuse me, to fight against a particular antigen. Here is the second exposure to this antigen that we're going to call A, and you can see for one, the size of the response is much, much, much stronger than the primary immune response. And it's also much, much quicker. Within a day or two, we're having this huge production of clones and antibodies to fight against this particular antigen. And so this is very much what the primary immune response looks like. A little bit slower, a little bit weaker, and this is very much what the secondary immune response looks like when we encounter that antigen again, because we already have the B cells that are memory cells that are already kind of primed for that particular antigen. We get a much stronger, much faster reaction. And so that's one of the major benefits to our adaptive immune system. So we can acquire humoral immunity kind of in two ways, both actively and passively. In an active type of immunity, it's when the B cells actually encounter an antigen and produce the specific antibodies against them. In passive immunity, the B cells don't get challenged, and so they don't get any memory cells. Really what we're getting, instead of the B cells being challenged with passive immunity, is we're already kind of just getting the antibodies that have been produced. And once those antibodies degrade, because they are just proteins and they will degrade, the passive immunity will go away. Both active and passive immunity can be acquired naturally and artificially. So if we look at the two branches of active immunity, naturally acquiring active immunity would be you got infected with something, and your B cells saw that specific antigen and started to produce specific antibodies against them, and also created some memory cells. Artificially acquired active immunity are things like vaccines, where we inject ourselves with kind of parts of a virus or parts of a pathogen, or maybe a dead pathogen, so that our B cells get challenged by these antigens and start producing antibodies and memory cells. In passive immunity, since the B cells aren't challenged, we don't get any memory, and really all we're getting in passive immunity is the antibodies that are the humoral immunity. So a really good example is from mother to fetus during the fetal stage, so via the placenta, or to an infant who is being breastfed. You have antibodies that go from the mother to the fetus via the placenta, and those will circulate in the fetal blood circulation for a while, and then also through the breast milk. So for several months after a child is born, if that child is breastfed, as it suckles on its mother's mammary glands, they're getting antibodies from the mother. This means that whilst the child is still being breastfed and whilst the child is still getting these antibodies via the milk, they have some naturally acquired passive immunity. But the child's own immune system has not developed an active immunity to these things, because the child's B cells have not been challenged. They're just kind of passively getting the antibodies already. Artificially acquired passive immunity is when we take the antibodies themselves and sometimes inject them into people to help them fight off particular infections. So two very different kind of arms of immunity, and you definitely want to understand kind of the differences between active immunity, where we challenge our B cells, they encounter the antigen, they produce antibodies and memory cells, whereas in passive immunity, it's really just getting the antibodies and skipping the whole challenging of the B cell with the antigen. But no memory cells are made via passive immunity, and so when the antibodies go away because they've been degraded, the passive immunity will end, whereas the active immunity, you've got it. If you make memory cells, you've got active immunity to that particular pathogen. Vaccines are a really common way that we get active immunity, and it's one of the reasons why they're so very effective, because they do challenge our B lymphocytes and we do make memory cells to them. Most vaccines that we get these days are what we call attenuated pathogens or even a dead pathogen, where they'll basically make it inactive. They'll pull parts of it off, or maybe they'll put in the vaccine a part of a bacteria or a part of a virus, and this allows us to see these antigenic determinants that are immunogenic, so that create our memory cells, without theoretically giving us the symptoms of the actual primary response. So you might feel a little under the weather sometimes, some of us, after a vaccine, but by and large they're very, very, very effective, and they've definitely one of the major strides in medicine. Polio, measles and mumps, although there's been some resurgence of that due to people who are choosing not to vaccinate their children, but definitely one of the best advances in medicine is this use of vaccines, so really quite important. So the antibodies are what give the B cells their ability to impart humoral immunity. Well, what are antibodies? Essentially, they're just the proteins secreted by the plasma cells. They do have this kind of Y shape, and they are capable of binding with a specific antigen that's detected by those B cells, and then kind of not directly destroy the antigen, but kind of tag it for removal. And we'll look at kind of the mechanisms for that in just a second. Sometimes we'll refer to antibodies as immunoglobulins because they are these kind of globular proteins. That's what globulin means, and since they're immune proteins, we get immunoglobulins. We have 5 immunoglobulin classes. They're found in different parts of the body sometimes, and really it's a matter of function. They respond to different types of antigens, and they have different functions, and we'll look at that in just a second too. So this is kind of your generic immunoglobulin or antibody. The antigen binding site is out here with the kind of V part of the Y shape, and the stem region down here, kind of the not the forked part of the Y, but the kind of trunk of the Y, as it were, is actually what determines which class of antibody that they belong to, and that class of antibody really kind of dictates what the antibody can bind to, and how that antibody functions to kind of negate the particular antigen that it processes and deals with. So there's a nice little table in your book, it's 21.5. You can review that as well for kind of the functions and locations of these various types of antibodies. We're gonna look at a couple. This one here, immunoglobulin M, is huge. For one, it's a pentamer, so you can see 1, 2, 3, 4, 5, and it is the first antibody that typically gets released. So very early on in the primary immune response, you're going to see lots of immunoglobulin M that's kind of circulating in the body. In terms of mechanisms, it's really good in agglutination because it's huge, and also kind of activates our complement system that we saw earlier. Immunoglobulin G is the most prolific in our kind of late primary and secondary responses, and it's one of the ones that can cross over the placenta and get into a fetus. So if a mother has immunoglobulin G to a particular type of pathogen, that can be transmitted to her fetus. The E class is very prevalent in terms of allergies and parasitic infections. It also tells mast cells and basophils to release histamine, so it plays a role in the inflammatory responses that we see as part of the innate immunity. So here's another example of adaptive immunity and innate immunity overlapping. These D-class immunoglobulins we find attached to the surface of B cells, and one of their main jobs is to act as a receptor for the B cells, so that the B cells can recognize different antigens. then the alpha class, the A class, is typically what we find in a lot of our mucous membranes. It's a dimer, so you can see there's two of the Y-shaped proteins. And since we do find it so very often in our mucous membranes, it's really helpful in preventing pathogens from getting kind of further into the body beyond and kind of stops them right there in the mucous membranes, as opposed to letting them get a little bit further. So as I said earlier, the antibodies themselves don't actually destroy the antigens. This is another kind of reason why the B lymphocytes provide humoral immunity. They will inactivate them, they will kind of pull the teeth out of them, as it were, and also kind of red flag them to say, hey, this is an antigen that we want to get rid of by some other means. There are four kind of main types of mechanisms that antibodies use to inactivate antigens, and let's look at those. So neutralization is for typically if a bacteria releases some sort of exotoxin, or if a virus releases some sort of toxin or part of itself, and that's what you're seeing here, then the antibodies will kind of clump around this exogenous toxin, part of a pathogen, and since they surround this pathogen, it basically prevents the pathogen, or the part of the pathogen, from then binding onto other cells in the body. So the toxin, or the part of the pathogen, is still there in the body. It just can't do anything because it can't interact with other cells of the body, because it's coated in these kind of neutralizing antibodies. Agglutination is typically for antigens that are bound to other cells, and so what will happen is these here's that immunoglobulin M. You'll see it'll kind of bind onto the different antigens of these different cells and cause the cells to clump. This is what we saw when we looked at the ABO typing. Precipitation is a mechanism of action for antibodies against antigens that are soluble, so able to be dissolved in a fluid, and it basically takes all of these soluble antigens and links them together into these big, huge complexes, and then these big complexes precipitate or fall out of the solution. Both neutralization, agglutination, and precipitation all then make it easier for parts of the innate immune system to phagocytize different parts, or the complex that is precipitated out, or the big clump of cells, or these now neutralized exotoxins. And so it's really the innate immune system that is kind of getting rid of them, but it's made easier by the action of the various antibodies. Now there are some antibodies that also activate and turn on our complement system, and then once our complement system is activated, complement also enhances phagocytosis by opsonization sometimes. Complement also enhances the inflammatory response by causing chemotaxis and telling mast cells to release histamine, and complement can make these membrane attack complexes that eventually lead to lysis of the cell. So there's really kind of four ways here that antibodies can play a role in keeping us safe. Okay, I'm going to stop there and talk about cellular immunity as a separate lecture, so that way the files are not ginormous and huge.